Alright guys, we're going to go ahead and finish up section 2.3. We had made it to part 2 and we had been looking at the graphs of functions to determine, to evaluate the function and also to determine the function's domain and range. Okay, and so now what we're going to do is try and see if we can figure out what the domain of a function would be just from the function itself. Okay, so not by looking at the graph of the function, although you could graph it if you wanted to. So yeah, we're going to be looking at functions in their explicit form. Okay, and really, guys, the majority of the functions that we've looked at, virtually all, well, I guess more or less all of the functions that we've looked at have been what we define as polynomial functions. Okay, and these are functions basically that just have different powers of x in them. Okay, so like some of those that we saw in section 2.1, those linear functions, they just had a single x, or like an x to the first power. Those quadratic functions that had an x to the second power, an x squared. The cubic functions that had an x to the third. Now I know we saw absolute value functions, and then we saw one case of a rational function. Okay, but in considering what the domain for a function is, you have to think about the domain as being the set of all the inputs. Okay, or in other words, the set of all the numbers that we can plug into that function and always get an output, or in other words, another number out of it. Okay, think about the juice maker example. Okay, the juice maker is not going to work for anything except for fruits, or fruits that can actually be juiced. If you try to put anything else into the juice maker, you're not going to get anything out, right? And so that's the way we can approach these functions. We have to be thinking about what numbers can I plug in such that I'll always get another number out of it. Or alternatively, it turns out it's actually easier to think of it from the perspective such that what numbers can I not plug into the function. Okay? Or in other words, what numbers would make the function undefined. And so there's really just a couple cases in which the domain is going to be anything but all real numbers. Most of the functions that we're going to encounter, their domains will be all real numbers. That just means that we can take any real number, plug it into the function, and it'll give us a real number out. Okay. The two cases in which that will not always happen is when there's an x in a denominator, or whenever there's an x under an even radical. And for now, guys, you can even just ignore case 2. Okay, we'll see this later on in the course, but basically the only time we're going to have a restriction in the domain of a function is when there's an x in a denominator. Okay. Otherwise, the domain of the function will be all real numbers. And so we've got a couple examples here. Example 3. It says, find the domain of the following function. Well, this first function right here is a linear function. It's 4x minus 7. And it is a polynomial. More generally, it's a polynomial. Okay. And so therefore, the domain will be all real numbers. So we can write this. You could write it in interval notation if you wanted. It would be negative infinity to positive infinity. Or the book is going to express it like this in set builder notation. And I'm not sure why I'm seeing double every time I go to write. Anyway, it would be all values of x such that, and then x, you just write x is a real number. Okay. And so this just means that you can plug any real number in for this x right here, and you'll always get an output. And that output will always be another real number. Okay? And the same thing for this function g of x as well. This is actually a cubic polynomial. Okay? So guys, you'll need to remember this throughout the course. The domain for any polynomial is all real numbers. That just means that a polynomial will accept any real number and always have an output. And so that'll be the domain for this one as well. All values of x such that x is a real number. Okay. Any real number that you can think of, if you cube it, multiply it by 2, and subtract 5 from it, you'll get another real number. Okay. What that real number is just depends on the real number that you plug in for x. Now, the exception to this is going to be a function like this one. Okay, and this is what we called a rational function. And if you remember, guys, we cannot divide by 0. Anytime you try to divide a real number by 0, there does not exist another number. Okay. In fact, if you try this in your calculator, and I think that we did this. Let's say the number 10, for example. Let's say I try to divide this by 0. Well, I get an error message, okay? Because division by 0 is not undefined. And so basically what we need to look out for is what values of x would make this denominator 0. If we can't divide by 0, then the only exclusion to the domain is going to be a value or values of x that make that denominator 0. Okay? Now in this one, you could look at it and inspect it and think, well, if x were 1, then I would have in the denominator 1 minus 1, which is 0, and so I would end up with 2 divided by 0, and that does not exist. Okay, it's not a real number. And so, therefore, 1, because it makes the denominator 0, would be excluded from the domain. So the domain of that function would be all real numbers except for 1. All right, and that's actually example 4. Okay, and so how do we write this? All real numbers except for 1. Well, the book will do it like this, I believe. The domain will be all values of x such that x is a real number and x cannot be equal to 1. Okay, that's what this symbol right here means, not equal to. So this just means that this function will take any other value of x and it'll always give you another real number as an output. Okay, except for 1. All right, now what about this second rational function right here? Well, again, the only thing that really matters would be values of x that make the denominator 0. Okay, so this one is not so obvious. And so when they're not as obvious, guys, instead of trying to think about it or guess and check, you can literally take the denominator, you can set it equal to 0, and you can solve it for x. And whatever number you come up with for x, that will be the number that's excluded from the domain, because that will be the number that makes the denominator 0. Okay, so in other words, I need to solve this equation for x. Okay, so I'll do it by subtracting 5 from both sides. If I do that, I'll end up with 7x is equal to negative 5, and then I'll divide both sides by 7, and I'll end up with x is equal to negative 5/7, so a fraction. So it's a fractional value that makes this denominator 0. And so because of that, it's this fractional value that we must exclude from the domain. So the domain will be all real numbers except for -5/7. And so again, I could write it in set builder notation and say the domain is all values of x such that x is a real number and x cannot be equal to -5/7. Okay. Now I do want to point out that you can also express these domains in interval notation, except you have to exclude this one number. So to express it in interval notation, you would get well, I wouldn't use curly braces. You would basically be going from -infinity up to that value that you're trying to exclude, and to show that you want that value excluded, you put a parenthesis around it. And then you use this symbol right here, or the book sometimes will have you put a comma instead of this union. This is a set operator. It allows you to join two sets of numbers together. So if the domain is all real numbers except this value, it would be all the numbers less than that value combined with all of the numbers that are greater than -5/7. And the way you would write it or express it is the second part of that set would go from -5/7 all the way to +infinity. And again, the fact that I'm using parentheses around the -5/7 intimates that I'm excluding that one value. Okay. Otherwise, the domain would just be negative to +infinity. But again, like I said, in this section, the book doesn't use interval notation, I don't believe. All right, so really the only time you're going to have exclusions to the domain will be if they are rational functions, or in other words, if there's an x in the denominator. The last case we'll see is example 5. Now this is an absolute value function. And technically, an absolute value function, well, let's see. I don't believe that technically it's a polynomial, okay? Although it sort of behaves like one. It behaves like two linear polynomials together, right? Because if you remember, it has that kind of V shape, so it's like, kind of like one line connected to another line, okay? And if you remember, we'll think back to this example too. The domain of this function is all real numbers, okay, because it goes off in both directions, to the left and to the right. Or you can analyze it and think, well, if I take any real number and plug in for this x, well, it'll become a positive if it's not already, and if you double it and subtract 3 from it, you're going to get another real number, okay? So the domain for any absolute value functions that we see in this class will also be all real numbers, okay? All values of x such that x is a real number. Alright, now we will see some other functions later. We'll see some square root functions. Their domains will not be all real numbers. And then we'll also see some logarithmic functions, and the domains of logarithmic functions are not going to be all real numbers. Okay. So anyway, that basically concludes this section, guys, in which we're focusing on determining the domain and the range of a function, whether it's graphed or in explicit form. All right, and so I'll see you in section 2.4.